welcome to this next section of day one. So today is a pleasure now to introduce the next speaker, Anthony Shiro, Vice President Quality and Sustainability at Navitas.
Hi.
Anthony, welcome on board. Anthony comes to Navitas with 15 years of quality, reliability, project management, process development, and design engineering and management experience in the power semiconductor industry. In addition, he has spent the past 5 years in the consumer goods electronics industry as Vice President of Quality and Reliability Engineering, focusing on system-level reliability and quality controls. Anthony holds a Bachelor of Science in Chemical Engineering from UCLA. Anthony will give us a lecture titled GaN Power Integrated Circuits Lead the Way to Sustainability and Deliver Carbon Neutral Status. After the talk, Anthony is available to answer you for any questions. Feel free to share any question from the chat on the right side. Okay, we can start. Anthony, thank you.
Okay.
Thank you for joining us, and the stage is yours. Thank you.
Okay. Thanks, Maurizio. Thanks for having me. And let me start my presentation here. I'm going to talk today about GaN power ICs and the impacts on sustainability, how they lead us to carbon neutral certification status as a company here at Navitas, and go through the quantitative data we have behind this sustainability topic with regard to GaN ICs. So next slide. Let's see. All right, good. So it starts with GaN, gallium nitride. So gallium nitride is what's called a wide band gap power semiconductor material. Gallium nitride has been used in different types of devices over the years. Navitas is powering and driving using GaN, gallium nitride, in the power semiconductor space for high voltage devices. GaN has some very interesting and incredible physical properties where it enables very fast switching. It enables smaller and lighter end applications. It allows higher efficiency and faster charging in order to charge your devices much more efficiently, better energy usage, and faster time from 0 to full charge. So it all starts with gallium nitride, and that's what we're going to focus on. It's been the material of topic since the company's founding, but it's only one type of wide band gap material. There are others, but we'll focus this presentation on gallium nitride's impacts. So Navitas' mission since being started as a company 7 or 8 years ago is to electrify our world. Power semiconductors are always about energy savings, improving efficiency, and as we move to transition from a fossil fuel-based energy economy to a renewable energy economy, Navitas sees gallium nitride and the implementation of gallium nitride semiconductors, as well as all wide band gap semiconductors, as one of the key driving forces in that transition. We have done extensive analysis to show that gallium nitride, when compared to silicon, has a much lower component carbon footprint than silicon does to produce. We also show that power supplies made with gallium nitride are about 30% more efficient and use less energy over their lifetime in the field as to CO2 footprint for chargers and adapters. And we've also shown how faster charging and more efficient charging can accelerate the transition from fossil fuel-based automotive to electric-based automotive by over 3 years, which makes a dramatic impact by 2050 in total emissions from within the automotive market. And we predict that GaN can save up to 2.6 gigatons per year by 2050. And I'm going to show you some of the data behind that. We've published our own sustainability report that includes 2 full years of data, and we're working on our 3rd this year. And again, I'm going to go through some of that data. So there's 2 key aspects to remember when it comes to gallium nitride and the conversion or transition from silicon devices to gallium nitride devices. Number 1, I will show you data that demonstrates how gallium nitride ICs can be up to 10x lower carbon footprint in manufacturing over the next few years. And we also partner very closely with our customers to help them design system levels that are smaller, lighter, less material, and at the same time more efficient by using the benefits of the gallium nitride semiconductor technology. And I'm going to walk through that. So there's 2 key aspects. One is material reduction and manufacturing impact reduction, and one is in-use reduction for our customers and the end users. So in order to quantify this, we have chosen at Navitas to take the approach of using a life cycle assessment, or LCA. Life cycle assessment is governed by several standards noted here on the slide, and our study is compliant with those standards and fully third-party approved. We have used a third-party company to do the detailed calculations because they're the experts in this area. And along the way, we've learned a lot about sustainability and life cycle assessment methodology. So in a sustainability assessment, the first key item you have to do is define your functional unit. So we've looked at what does it take to make 1 wafer, what does it take to make 1 die of both GaN and silicon high voltage power semiconductors. And we've also looked at when you put those components into an optimized power supply for 65-watt USB-C charging, what is the total impact of that charger over its lifetime powering a laptop or notebook computer? And I'll show that data here in the next few slides. The second key aspect to a life cycle assessment is defining your boundaries. So in our boundaries, we've chosen the full, what they call womb to tomb assessment in our life cycle. And that means we start from raw material extraction and go all the way through component manufacturing, charger manufacturing, distribution, end use, and meaning the use phase of the part, and the end of life disposal of the end product. The key point of this study was really defined what are all the benefits of gallium nitride, and look for any negative impacts of gallium nitride to make sure we had a full assessment of the new technology. So the first step here, as you can see on the left-hand side, is looking at gallium. Gallium is a key aspect of the new technology, and gallium comes from many places around the world. You can see from the U.S. Geological Society, there are many deposits of gallium, and gallium comes from the mining of bauxite in order to make aluminum, and it's a natural byproduct of that process. So gallium comes along with that mining, and it comes along at the rate of about 350,000 kilograms per year as of 2019. And on the right side, we compare that to the use of gallium. So our estimates show that for each device uses about 350 milligrams of gallium per die. So if we consider that we need to make at scale, if we just take a round number of 1 billion GaN chips a year, that's still only about 40 kilograms of gallium. So you can see that that's a much, very tiny number compared to the total reserves and the total produced per year of gallium. And the reason for that is shown up in the upper right-hand side. So Our technology is a GaN-on-Silicon technology, and silicon means the silicon substrate. So on the left-hand side, you can see that a typical high voltage silicon MOSFET will use a silicon substrate with silicon epi layer or epitaxial layers on top of the substrate, whereas a GaN material, GaN-on-Silicon, will use a silicon substrate with a very thin layer of GaN epi on top of the device. And this, as you can see, makes those devices mostly similar in terms of materials, and only a small amount of the silicon is replaced with gallium and gallium nitride. So from this first part of our life cycle assessment study, we can see that there are ample reserves and very little replacement of silicon. So they're expected to be very little difference in benefit from or impact from GaN versus silicon-based devices from a raw material perspective. Next, we look at the wafer fab process. So generally, the wafer fab process after the epi material is relatively similar. The big difference between today's typical high voltage MOSFETs is that generally they will be made on 8-inch wafers, whereas our GaN technology that we use today is made on 6-inch wafers. So we've made our comparison based on today's standard or norms. Even at that 8-inch versus 6-inch, an equivalent performing GaN device still has about 70% more die per wafer than the equivalent silicon device made on an 8-inch wafer. So that big difference in die per wafer makes a big difference in impacts. In addition, with a step-by-step process in the wafer fab analysis, on the left side here, we can see that even on a per wafer basis, comparing that 8-inch silicon wafer to 6-inch GaN wafer, we see over 50% reduction in total energy use required when we stack side by side a silicon wafer process versus a gallium nitride wafer process. And when you take into account the 70% more die per wafer, you get a dramatic reduction in the total impacts. That's about a 70% reduction in total impacts of producing a GaN die versus a silicon die. And that doesn't just go for energy or greenhouse gas related, that applies to every category. Chemicals and emissions from chemicals, water use, which is always a big factor in semiconductor manufacturing, and other metals and materials. There's across the board, due to the smaller die size, there is a significant reduction in impacts across all the different key categories of impacts looked at in our life cycle assessment. Next, so when we combine that, so that's today, but since silicon is a legacy technology, it is improving very slowly at this point and with a lot of cost to make improvements. But gallium nitride is still in its early stages as a technology. And so our plans show us to take this 4x, what is today about a 4x reduction in carbon footprint versus a equivalent silicon component. We believe in relatively short term, over the next 2 to 3 years, we will realize a 10x reduction in based on our planned roadmap and technology improvements. And of course, it's all driven by the same thing: smaller die size, primarily, along with that reduced amount of total energy needed to produce the GaN part. So that's the device level. Next, we look at that third functional unit, which was the charger level. USB-C charger here, we compare a silicon-based 65-watt USB-C charger to a GaN-based 65-watt USB-C charger. This is a design that was done in the 2020 timeframe, a couple years old now, but it demonstrates the benefits. So what you can see is we do a component by component, material by material analysis of each of these chargers, and we stack up all the impacts of each component and material to do a comparison. That comparison shows that there's about a 30% reduction in total impacts due to size, weight, and material use alone. We expected to see a material reduction, but we didn't know how to quantify it. So this life cycle assessment methodology gave us a way to actually quantify the total impact comparing these two chargers. And that 30% was mainly driven by the reduction in PCB size. Plus, it was driven by the fact that Navitas has a unique approach with GaN-based ICs integrating multiple functions into the device, which allows for a significantly reduced component count from silicon or even from discrete GaN devices used to replace silicon. So our reduction here we've shown and calculated to be 30%. So that's manufacturing materials related. The next big case, which was, the primary aim of the study, was to look at the use case scenarios. We want to calculate what's the benefit due to improved efficiency of the gallium nitride switch. And so what we did was we tried to come up with 4 different scenarios that would encompass all the different possible, or many of the different possible use conditions we could imagine. So we came up with the business travel, doing business at home, doing business in the office, and a personal home use of a notebook computer. And all our, the detailed breakdown is shown here, but the main differences are how much time are you plugged in using full 65 watt power to charge your device versus how much time are you plugged in and just using like a trickle charge to keep your device and battery fully loaded. And this is just different ways of looking at that across those 4 different scenarios. And what this shows here on top, we're looking at use in countries that use low line input voltages, 110 to 120 volt type voltages. And on the bottom, we're looking at countries that use high line input voltages, so 220 to 230 to 240 volt type conditions. And what you can see is across all 4 cases and both the different types of geographies and input voltages, in all cases, gallium nitride is more efficient and a reduction in impacts. If we look at one of those cases in particular, we chose this case, the work travel scenario, because this case highlights the most charging at full power. And it shows that on the lower input voltage countries, that you see about a 30% reduction in total impacts. And on the higher input voltage countries, you see a 10 to 15% improvement. And that's just based on how the device was optimized and for what regions of use the device was optimized for. Every power supply can be optimized differently for high power charging, for no load or light load charging in order to accomplish the goals that the design team is working on at the power supply manufacturer. But in this case, this is the result that we are able to calculate and report. So overall, what does that come to? This again shows the overall assessment. It shows that the most important factor in moving from GaN to silicon is the use phase energy savings, which is calculated as 2.5 kilograms improvement in CO2 equivalents across the lifetime of the device, and at 2.5 kilograms. But interestingly, we also found that it's very significant, 2.1 kilograms reduction for every device made due to material and distribution impacts due to lower size, lower material count, and lower weight. So both are interesting and appreciable to the net result of over 4 kilograms CO2 saved per device that we ship from Navitas. And here's a high-level view of what I've just stated, how gallium nitride shows a much lower, 4 to 10x lower manufacturing impact. And when you combine that with the lower material impacts and improved efficiency impacts, you can see that there's over a 4 kilogram net benefit from transitioning from silicon to GaN-based semiconductors. So that's one aspect. One aspect is what are the benefits our products provide at Navitas. The other is how much impact do we have? So we have an aggressive reduction in our corporate emissions goals. In order to do these calculations, we again decided to use a quantitative approach and use a life cycle assessment to assess our full organization and the impacts our organization has doing business. And as part of that impacts, we include all our corporate offices and all our offices worldwide. We include all the manufacturing impacts at our suppliers, and we include all the use phase impacts of our devices. And with that, and with third-party expert support from Earthshift Global, we have come up with our organization, or LCA report. We've done that for 2 years in a row now, and we're working on it this year to be our 3rd year. We have an aggressive, or we've demonstrated the ability to reduce our carbon footprint intensity over the past 2 years, and we'll show that again in our 3rd year. And we'll continue reporting this quantitative measure to hold ourselves accountable and stick tight to our values of Navitas in electrifying our world and being having a good impact on the transition to net zero across the world. So, by doing this quantitative assessment, we were able to combine the low manufacturing impact of gallium nitride devices, our low corporate carbon impact due to our low carbon business model and our efforts in reducing our carbon footprint, while investing in renewable energy infrastructure in order to be certified as a carbon neutral company by Natural Capital Partners and their carbon neutral certification, making Navitas the first semiconductor company to achieve that carbon neutral certification. So this is where I want to recap in summary that low manufacturing impact from 4x to 10x reduction due to producing gallium nitride based power semiconductors versus equivalent silicon semiconductors has one major impact on our total carbon footprint, and our quantification and low corporate carbon footprint business model has allowed us to become carbon neutral certified. So beyond that, we want to look at, well, what impact do we have in use, in savings? Those savings I talked to you about of 2.5 kilograms per unit shipped from efficiency improvement and 2.1 kilograms per unit shipped in material reductions has shown that for our devices as used in the field today, we have just recently, over the past 2 months, reached 100,000 metric ton CO2 savings. So we track this as one of our key corporate metrics. To be honest, this is a relatively small number compared to all the carbon impacts in the world. But we're just at the start of the transition from silicon to GaN. And we are just at the beginning of that transition for all wide bandgap materials. So what is the potential? What's the possibility that we can do? If we look at just the overall mobile electronics market, 100% conversion from silicon-based material to GaN-based material can deliver over 10 billion kilograms of CO2 equivalent savings based on our analysis. And so our goal at Navitas, and what we're working closely with our customers on, is to accelerate this transition. That number of over 10 million tons of CO2 is a significant number each year and will only grow as we go to 2030 and 2040 and 2050, and provides quite a positive impact to the world, just considering mobile, which is a small portion of electronics usage globally, and but makes a big impact. And GaN conversion from silicon to GaN will continue to make a bigger and bigger impact as it goes into all the different end markets of power supply around the world. So that's my last slide. And now I guess we'll open it up for some questions.
Thank you, Anthony. Thanks a lot for your great talk. So I have just, we have a couple of minutes for the questions. So I have a question for you. You talked about gallium nitride, GaN, of course. So do you expect GaN to go beyond higher voltage competing with silicon carbide, for example? Which is, so what would be the future in terms of vertical, lateral technology and limits of integration? What are, if there are?
Yeah, okay, so gallium nitride, so at Navitas, we have both gallium nitride and recently silicon carbide technologies in our portfolio.
With the last acquisition.
That's right. So we are looking for using the best technology with our customers. What will solve their problem the best? What will give the best energy efficiency? And so when we look at that, today, lateral GaN-on-Silicon is really optimized for integrated circuits and integration. That's the best way to do it. And it's optimized up to 800 volts, which is our current GaNFast power IC technology. Above that, silicon carbide today is a pretty established technology. While there are some other wide bandgap technologies that are out there, many of them, GaN-on-GaN, vertical structures, many other potential technologies in the future. At Navitas, we would be interested in seeing how all of those come to fruition and come to the market, but most of those are really in academia, still not proven in the market. So as they develop, Navitas would definitely be interested in pursuing whatever will give our customer and the planet, better use of electronics to move from, fossil fuel-based economy to an electric-based economy. But so for now, we see GaN really, taking over the market below 800 volts, and silicon carbide really establishing itself as the go-to material for higher voltages than that, and really phasing out of silicon, but so that's where we see the market going right now.
Okay, thank you. So another questions or comment, if there are plans for moving from 6-inch fab to 8-inch to further improve the material cost saving in die per wafers?
Well, I think you do see some GaN companies today talking about 8-inch and working on 8-inch. And so that's an obvious next place to go. It will further improve the carbon footprint impacts per device, as well as total cost capacity as a important next step in the technology. So we definitely see that on the roadmap.
Okay. So in terms of manufacturing between GaN and silicon carbide, we know that silicon carbide should reach higher temperatures compared with GaN. So please correct me. In terms of renewable energies that can help in the manufacturing, just with a green vision, what are the differences? So GaN is better in this case or no? So how can renewable energies can help in the manufacturing of GaN? So,
yes,
for example.
Right. So I think renewable energy, so first off, about 90% of the impacts of semiconductor devices are in the wafer fab process, both starting material and wafer fab. So that's the key focus. So getting renewable energy into wafer fabs would have a very positive impact on every semiconductor technology. And I think the difference we see between silicon and GaN would still be essentially the same, but based on a much smaller number when using renewable energy. So I think the driver, some of our partners, our main partner is very big in use of improving their sustainability impact and use of renewable energy in their operations. And as more and more renewable energy capacity comes online, I think it'll help everyone, including GaN, including silicon carbide, and even including silicon in reducing total footprint of semiconductor devices.
Okay, so we are in conclusion. Thanks a lot. Many thanks, Anthony, for your presentation, your great talk, for introducing Navitas technology. Thank you. Thank you, Anthony.
Thanks, everyone. Thanks,
And
Maurizio.
thank you. And so we are at the conclusion of this day one, but stay tuned with the agenda and also with tomorrow about agriculture. Thank you, everyone. Thanks a lot for attending. Thank you, Anthony. Bye.